All right, so we're today talking about numerical derivatives. Numerical integrals. So along the lines of well, in basic stuff, first is just a recap, just in case I'm going to use the material in some other course. So derivative shows how the function changes, and integral is what corresponds to a change. But then when we have well, that's the part for instantaneous or indefinite integral. And then when we have a definite integral, it's from some point to another point, calculated that way by regular integrals or antiderivatives, but we can also interpret the integral as an area. And are we having more people? Hello, welcome. We just started talking about integrals and how to do them numerically. Okay, folks are coming from the exercise. Welcome. So just started about integration, and the intro I had when I arrived on the hall was that now we're going to try to see how we do integration for real, because in many cases, especially if you're creating a signal, then you actually, in many cases, you don't even know the function, or the function might be difficult to integrate, and it's faster just to calculate a bunch of data points, and then based on those data points, estimate what the integral would be based on the interpretation that integrals stand for an area, or with more dimensions, maybe volume or so on. It's a bit harder when we go to more than 3 dimensions. And think what it corresponds to, but 2D integrals, what we've been talking about, correspond to an area. 3D integrals would be corresponding to a volume. And of course, it's not completely area, because if you think about an area, then, well, last time we had this note about the triangle inequality. So if we're talking about the area, then strictly speaking, area between the axis and a function would be the sum of t's. So now when we look at the definition of the integrals, I'm going to stop sharing the screen for a moment, so you can now should be able to see my video. So now this part here, it's completely invisible in the room, which someone maybe drop the lights off a little bit. Well, there's another light switch behind your back, so press the down button. Nope, that's the reserve button. Just use the lights. Okay, let's press 2. So now, when you have numbered buttons here on the wall, it's light settings. 1 is full lights, and then lower and lower. Okay, now maybe we can see same screen in the classroom as well. So, or I could point out stuff from. I wonder if this laser pointer has batteries. It does not. So okay, that was useful. So these parts are all of the area, but now that this part is below the axis, then it actually is a negative area when we consider the integral. And actually, I'm not sure if Octavia and Tara on the net sees my mouse cursor. Of course not, because it's on the camera. And oh, on button. Okay, so now we can see it. So these are the positive parts, but if we use the interpretation of area, this would be also area between the curve and the axis. But when we integrate area under the axis, then that one is kind of a negative area. So if you are strictly interested in knowing the absolute area there, then we need to find these points and then or integrate the absolute value of the function. Mike's also there. Hello, we just started on basic intro on our theory on what an integral is and the explanation of integral as an area. And now, one way is that we could fill it with boxes that fit under the curve. Well, that's the so-called minimum interpretation of doing the boxes. And then the smaller boxes we put there, then the closer we are to the complete area. And there are different ways of filling. So we're gonna first have some look of those. Oh, one more thing we can calculate the integral. This is how we calculate the length of an arc. So what this considers is what would be the length of a short section of the curve, and when we go to really short sections, the derivative here pops up. So it is kind of a length of a really short section of the curve, and then applying Pythagorean theorem. And then when we integrate over these really short sections, we do get the arc length of the curve. And summing up those short sections is the same thing as integral. Numerical integral, so we do have previous definitions that show us a way of estimating. So if we don't go to infinitesimals, which is the name for those really approaching zero sections, then we can also calculate integrals. So the Riemann integral assumes we can find the mean value, or then taking limits that we take the minimum value of the interval, maximum value of the interval, and then when we squeeze them together, so smaller and smaller intervals and the minimum maximum are going to approach each other, and we're gonna, by squeeze theorem, we're gonna find out the actual value. Then there are different ways we could also estimate the area. So if we don't know the minimum, maximum, or the average values, then we could maybe think that maybe the function value at the start or the end points could be a good estimate. Those are usually simple because if we have calculated function values at the interval, that's a really simple thing to do. The middle point is actually usually slightly more accurate. And then we might take an average of the endpoints, which is functionally the same as fitting a straight line in the chair. So fitting a trapezoid into that part. And then Simpson's method is fitting a parabola. So essentially, if we take some constant value estimate, so endpoints, middle points, that is saying what if our function was constant, then it would be really easy to calculate functions by summing up the boxes. Then if constant isn't good enough, then we might want to fit a trapezoid in there. So that is essentially assuming that what if our function was a straight line, maybe it has a good enough approximation, and if we're having significant curvature, then Simpson's method assumes that what if our function had some curvature and we estimate that by fitting a parabola or a second degree function. And some of those, for example, Simpson's method for many functions does work really well without dividing to sub-intervals, but we can further then reduce error by dividing the function into smaller intervals. So that way, even if we're having a little bit of error, then when we have smaller intervals, typically the area between the curve and our estimate is quite small. So but we then need to calculate more values of the function. The rectangle rule can be stated as this: if we start from the midpoint, from the beginning point, we get this. Similarly, we could take the end point, so we get fb times b minus a, which is just one estimate for the value of the function times 10 the width of the interval. So 8 times base is the volume of the rectangle. Simple deal. And if we divide that into parts, each with the width of h, then we get h times. So h is now here the common term. We get the value of those functions times h, but we can take h out of the sum notation because it's a common term for if it is common. In many cases, if we integrate a signal, so integrate any kind of measurements, you need to remember that even if we're supposed to have constant measurement rate, it occasionally fluctuates, and you need to check first if it's true that all the measurement intervals are the same, or if there's any fluctuation. So if we are integrating a signal, things might happen that h is not constant. And of course, the more subintervals we use, technically speaking, technical truth, the best kind of truth, we get more accuracy. But when we go to too small h, we start getting rounding errors, and then we lose accuracy. So there's some kind of a golden middle way. Depends on what kind of a computing hardware we're using. Midpoint rule, so similar, but now we need to calculate function values at the middle of those points. And often you see this formula stating this nk, which stands for the midpoint of the interval, which is xk minus 1, so the beginning point plus half of our step h. So it's relatively common in these methods that if you see h, it stands for step length. Usually assumed to be constant, but in practice not always constant. Rectangle rule has a little bit of error, so okay, what do we know? It assumes that what if our function was constant? So if our function is not constant, there's an error. What's the measure of not being constant? Well, that's called change, and change stands for derivative. So half of the derivative times the square of the interval length is our error estimate for one interval. And then if you use subintervals, we get this total interval, and then one component is what our subinterval length is. So how many of this kind of calculates how many of these subintervals we get and what's subinterval length. And this, again, we're having, same as in the previous lecture, we're using this capital X here. So it is some value. So if we want to establish a higher bound or upper bound for the error possible, we probably don't know what the average value would be, or the mean value, which would tell us the accurate what the error really is. So we typically try to figure out what's the maximum possible differential there and use that as an upper bound estimate. Use the midpoint rule. This gets interesting because with midpoints, we're estimating the change within the interval, or the average change, which is the first derivative. So then if it curves, then we're getting a little bit of more error, but we need the second derivative, or estimate the second derivative to estimate the error. So we get h squared. Of course, with the midpoint, if we already calculate the endpoints, then we have extra function evaluations needed. But if we can do that, then it's relatively simple. And do note that the multiplier is a lot smaller. So with the subintervals, we're still having 1/2, so half of that, and with the midpoint rule, it's 1/24, so significantly reduced error. And if it is a linear function with the midpoint rule, we actually do not have an error because the second derivative of our line is, we differentiate a line once, we get a constant, we differentiate a constant, we go to 0. But if you have a quadratic function, so second degree polynomial or something else which curves, then with the midpoint rule, we do have still some error. This also ties with what we were talking earlier with estimating functions. So if we have estimated a second degree function, then we're getting constant error with the midpoint rule. If we have estimated the function with a linear function, then with the midpoint rule, we don't have any error. But of course, with the linear function, we can calculate the area really simply because it's a triangle, or a trapezoid actually. Okay, so trapezoid rule. What if we had only straight lines? So this gets similar accuracy to the midpoint, but we now only need to calculate the endpoints of each interval. So with one, so this is the area of a trapezoid is the area of the triangle there on the top plus a rectangle, which will reduce then to this. So we need the endpoint average of the endpoint values times the length of the interval. And then if we have more than one interval, we get this out h, which is the average length of the interval times the point, sum of the points of each interval divided by 2. And now if we do it like that, we need to evaluate for each interval 2 function values. But if we notice that the endpoints that are also beginning points of interval, we can recycle those and we get the third equal, well, that's an estimate, not an equation. Just this is approximately sign, not equal sign, is the average length of the interval divided by the first point by 2, and the last point we need by 2, and then the midpoints can be just summed up because we need half of each for each interval for the average, but half of the end of the previous interval plus half of the beginning of the next interval is just the full value of that point. Okay, what kind of error? Well, here we see that actual multiplier isn't as good as with our midpoint rule, which we had here, but otherwise we're getting a really similar formula. We need the second derivative and then something that's on the cube of the length of the interval. And if we have subintervals, do note that subinterval length is more important than the full length of the entire integration interval. And the curvature here means, so we're estimating function as a linear function, so if it curves, that is, if we have a second derivative, then that's meaningful for the error. Again, this capital X means largest, the value of X where we have the largest value of the second derivative that forms the upper bound. Simpson's rule, okay, now we go, the definition of this starts from a zero-centric function. So from minus h to h, of course we can shift functions around. We had that on one of the exercises. Well, on the different derivation side. and we try to fit a parabola here. So we have a generic formula of a parabola is px squared plus qx plus r, where p, q, and r are some constants, and we fit that to minus h, 0, and h. So we've formed that this way, so it's easier to then we're going to have some of the values cancel out. So now we get at this system of equations where when we have 0, then we just get the constants, and then on the other points we get minus qh and plus qh, which are going to cancel out each other. Then we have the if we sum these, and then we get second degree terms. So now we can reduce the amount of constants we need to fit when we selected this kind of integration interval. So we get 2ph squared plus 6r if we're going to add y0 plus 4y1 plus y. Okay, so this is one way to calculate the number of those points, and why we did select that kind of a strange sum is because now if we replace fx with this formula and integrate it, now here we see the dash notation, so minus h to h. So integration was 1/3 px cubed minus plus 1/2 qx squared plus rx. Because we have different integral, we don't need plus c. And then a few steps, we after we put those h's and minus h's there, we get that kind of a formula. Take the common terms, or put back what these are, and we see that this is equal to 1/3 times h, y0 plus 4y1 plus y2. And hey, that was what we just summed up. And here's an estimate for the integral there. Now these y0s, y1s, y2s, we know. So we can state that as what we calculated, and now if we can calculate the function value, we can state those values. So we can skip the integration step. Everyone following? Hopefully. So essentially, when we calculate the value of this part here, we end up getting this. So some stuff cancels out, and we notice that this 2ph squared plus 6r is the same as this what we calculated. So it's y0 plus 4y1 plus y2. So we replace the y0s, y1s, and y2s with function values, and we get this formula. And because here the interval length is 2h, and when we put b minus a here, we need to have, and it was h, so it's we'll need to divide it with further 2, so halve it, so that's why it gets minus 1/6. And if we have only one interval, that's the upper formula. We should get more accurate results if we calculate that for each subintervals, and then we get this error formula, which has the fourth derivative of f and 1/90 as the constant, and the fifth power of the half of the interval as the interval related error. So how do we have, if we put this subintervals, what happens? And now, okay, we have this h here, h/3 again, and now what we're having was that the midpoint of each interval here is where we have the 4, and now we get 2 x2s because that's the beginning of the second interval and end point of the first interval. So there, we have on the midpoints, we remember that every second midpoint is kind of a, or internal point here is the midpoint of an interval where we fit a curve, and then one is the kind of a sub-interval endpoint. So we are getting this kind of a formula where to draw alternating fours and twos and so on. Also means that if you say it like that, you cannot have an odd number of those intervals. It also needs to be even. Or it might be possible, but then you'll need to then calculate the midpoints so that you can use this kind of a formula. The error of this, now remember we're having half of the interval length there. That's pretty small. And now also that we have the fourth power here, so the fourth degree derivative from error term. So Simpson's rule, which can individual sections can curve different ways. That essentially tells us that we can estimate accurately relatively high amounts of curvature. So changing curvature direction. Okay, so that was the basics, and I thought I might want to show some of that in practice. So usually you do have, we had a power curve example here. Do we have already a fun? Well, let's just run this. We get something. Do we have a function here? Now we get the fit. Let's make a function out of this. This is, by the way, the same you have on the exercises. So you could make a function out of that in this way. It's power. And now this at defines that I'm working with the function handle. And when I'm don't giving a function name, just giving parentheses which have the variable in them, I'm telling that it's an anonymous function which is then defined by what formula is here. And rev is now our variable. And these are using the fitting tool, so it has given us some variable named f, which has subcomponents of p1, p2, and so on, which are the coefficients. So now I can state something like power 200, which is 28.7. Let's see, power 344 should be relatively close to 60. Yeah, it is. Okay, and now we'll calculate a number of, so let's say x equals from 0 with each 0.5 to, let's say 600. So we have a relatively tight amount of grid there. H is mean difference of what did I name that? X. Okay, it's 0.1. That was used because I knew that, but just one way to calculate if you don't know what it is, and you have just time vector, you could calculate it like that. What's the average H there? And now I can calculate the function values, so power x. And the way I define the function, this should work so that I can give it a vector list of numbers, and I get in response a list of values. So that's one of the powers of MATLAB. So you can also give a list of numbers of vectors to functions, and we get out a list of all vector of results. Okay, and now if I want to know what's the integral, there's a command named traps, which is trapezoid method. It's not kind of a cool way to say traps. No, it's a trapezoid method. Just the y assumes we have a constant interval there. So I could say that integral is perhaps y times h. Yeah, that works. Or I can define points. So I2 is perhaps I almost made a typo there. Yx, which defines the time vector. And something went wrong because these should be the same thing. Okay, now what is wrong? Oh, it's xy. That explains. Yeah. A case of read the manual. Okay, now we got the same result, which we should. And we could also define some other than linearly spaced ones. So in space can create linearly spaced thing, but we could, for example, for some reason do t time is or whatever log space from 100 to 1000. Whoops. 100,000, and let's give us 10 values. Okay, infinity. Let's read the manual again. That was not supposed to happen. Why do we get infinities here? Oh, it's in the power 10 to the power of 1. Okay, so 1 and 10 maybe. Okay. Good to read the documentation once in a while. So we got to now these are not spaced that nicely, so we can have y2 power t. So we get values here. What was this? Yeah, it's just t. Oh, really small ones here. Yeah, okay, those are really small ones. Not nice. And now there's a difference. If now we cannot do just perhaps y times this probably has some inaccuracies compared to perhaps x, y. Yeah, significant one. Oh. C, y2. Yeah, entirely different things. So now we need to specify the time vector when it's not constant, especially when it's not constant in a really not so nice way. Quite often happens with data. So I have a demo data somewhere here. I did not. But that's kind of what we need to take into account here. And this software probably can take it into account that if we're trying to do really small h's. So for example, we had this X was each tab, but if we try X2 is, well, X3 is clean space from 10 to 1000 and some ludicrous number. Does this even calculate that? Maximum variable size, but the program is exceeded still. Still okay. Let's give you just like a still okay. Okay, now it does have a nice H of, just gonna take a while, H of approximately 1 millionth part. And let's see if something funny happens. So Y3 is power X3. Ouch, just gonna plot it. Sorry. It's gonna take a while and it's gonna take a while plotting it. Maybe if this keyboard had a button to cancel this, I would do so. But the problem is this keyboard doesn't have that button. I'll do it from here. No, I don't have power pool. And there's no button. Okay, there we go. Whoops. Hopefully no one is epileptic. So, okay, in MATLAB, when you put a semicolon, this doesn't happen. It doesn't print everything to string. Am I allowed to just cancel this now? No. Well, the laptop keyboard doesn't have a break button. I could otherwise stop this by pressing Control break, but the button doesn't exist on the keyboard, so yep, this is going to take a while.
Does Control Z?
Yeah, Control Z does not. Control C. Okay, Control C was it. Do we still have this? Yeah, Y3 does still exist. Okay, and now this probably works. Times H3. But if we did this in a loop, then we probably would have rounding errors. But I assume that traps is done well enough that it can ignore this. Now this is still gonna take a little while to actually get that. Hopefully this doesn't really affect Zoom because I'm going to tell oops. I usually have small details for you, so I ended my MATLAB session. Okay, so what I was trying to demo here is that when we sum up really small slices, we have to start getting rounding errors, but maybe time not to do that. this should happen, but well, this takes time for computation. Do I want to do it again? I should have programmed this previously with the intermediate saves. All right, so I'll maybe prepare ready code so I don't need to do debugging live on the lecture to have a demo of that. I should have numerous examples from research that were actually making a little algorithm mistake can affect the results. Just need to pick one of those, and then I could demo this on real data. But for now, this is it for how to apply numerical integration. We probably are not going to do these programming tasks on this course, but it's going to be relevant on integer mathematics too, and also computational software. Any questions at this point? Exercises should have been relatively simple. In the original version of the exercise sheet, there was a little mistake, so it actually takes one more iteration in problem 2 than I had originally. Do also, if you haven't done them yet, read the hints at the end of the sheet. So this helps a lot that on the bisection search method, when you're doing manually, you can compare to 60, which was our objective value. You can compare if you're getting higher or lower, but with Newton's method and second method, which are strictly for looking for the root, that is looking for the value where the function is 0, then you will need to shift the entire function down so that the method works. Any questions from the internet?
No, everything all right.
All right, so then we'll actually call it a day for today. Also, the plan for next period will be that these demos will be somewhat short. So probably closer to one hour or one lecture, and then our Wednesdays will be maybe a bit longer. And do note, if you didn't notice previously, we have a timetable change for the next period. When it comes to this part,